All right, let's get these last couple questions knocked out here. So this one's kind of funny because it tells you that the force of static friction max between these two is 12 newtons. All right, we want to pull the bottom one such that the force of contact here does not exceed, excuse me, 12 newtons. So that's hard to figure that out from the way this is worded, but we're just going to have to figure that out together here. And also, you pretty much, I think we're going to have to figure out the acceleration here pretty early on. So, excuse me, this being a separate part really doesn't make much sense. But anyway, here we go. All right, so let's draw force diagrams for each object. We'll do the 4 kilogram block first. So when in doubt, when I don't know what to do, just start with a force diagram. So it's got a normal force holding it up. It's got a force of gravity pulling it down. Now this is a bit weird here. The force of friction is pulling this block forward. Excuse me. Oh, I can't pause this video of the iPhone for some reason. But anyway, I'll soldier on, hopefully not sneeze again. So the 5 kilogram block also experiences that frictional force, right? So it is getting pulled backwards by that same force of friction. So when you pull block 5 forward, the friction due to 4 is pulling back on block 5. It makes block 5 feel heavier. That's what makes the 4 kilograms stick to the 5, making it feel like you're pulling 9, which you are, right? And then we have the applied force, F. Now, this one's normal force here. I'm going to call this FN4, I guess. The normal force on 4. FN5 is going to be pretty big, right? Because it's got to count for both objects' weights. So we have, I'll call this FG4. So FG5, its own weight is pulling it down, but also the contact force with block 4 is pushing it down. So that's actually the normal force, FN4. All right? All right. So what I want to do here is set up Newton's second law. All right? So for this one, sum of the forces in the X equals 4 kilograms times A. We don't know what that's going to be. So it's the force of friction, which is mu times Fn4 equals 4 kilograms times A. All right. Fn4 must be equal to the weight of that object, so 40 newtons. So right away, I can immediately figure out, oh, I'm sorry. You don't have mu. Oh, this we know to be 12 newtons. That's my bad. Equals 4 kilograms times A. So we do know A right away. 12 divided by 4 is 3 meters per second squared. So we already have that. I got to eliminate this as a part, right? We got to find that pretty much right in the beginning. So we know that 12 newtons of frictional force is what we want pulling block 4 forward. So 12 newtons, 3 meters per second squared. Now let's go see what that makes F. All right, so sum of the forces in the X direction for F is 5 kilograms times A. So it's F minus the force of friction equals 5 kilograms times A, which we now know. So F is going to be equal to 5 kilograms times 3 meters per second squared plus 12 newtons, that force of friction. So you end up with an applied force of 15 plus 12, 27 newtons is what it would have to be. Kind of a weird question. Not my favorite, but kind of interesting. I probably would just ask you to determine the acceleration of the system. Now, I had some students say, well, why can't you just use the blob method? Well, the problem here is if you use the blob method, right, and you say, all right, say this is all just 9 kilograms being pulled by some force, right? Well, I still would have to find the acceleration of the system first, right? Right? Can't use the blob method without finding A first. If you find A first, knowing the force and the mass of this one, then yeah, you could say, okay, you know what? I do know the acceleration. It is 3 meters per second squared, so F equals 9 kilograms times 3 meters per second squared. That is 27 newtons. Yeah, you could do that, but you have to find the acceleration first. You can't find the acceleration right out of the gate with the blob method because the only thing you know is the total mass. So you got to look at one of the masses first, the little mass first, to get the acceleration. Okay? All right, next one quick. This one I like quite a bit more. So this one always gives students a bit of trouble. So you're pushing on the little block fast enough so that it doesn't slide down. If you go too slow, it's not going to generate enough normal force here to produce enough friction to hold it up. So the key here is that you need to push it hard enough, fast enough, so that the resistance of motion of block M, the big M, which is heavier than little m, you know, that normal force pushing big M forward reacts back on little m strong enough to provide enough friction to cancel out gravity. But if you don't recognize that right out of the gate, just start with the force diagrams, right? So I'll make a force diagram for little m first. All right, little m has got this applied force, capital F, acting on it. It's got negative mg trying to pull it down, little mg. It's got a force of friction holding it up, and it's got a normal force pushing back on it. Now, we called that force of big M on little m. I'm just going to call it a normal force, and then I'm going to say that normal force is what pushes big M forward. So then we got big M. All right, so big M has its mg, a little bit bigger, right? It's mg, negative mg is going down. It's got, also pushing down on it, it's got the same force of friction. That force of friction that holds this up pushes down block M, right? It makes M seem heavier. So then there's Fn on big M, I'll call it. I call it Fn1, Fn2, I guess. And then the normal force, contact force here, is what is propelling big M forward. So I'm just going to say Fn. M doesn't have any forces going to the left. There's nothing resisting its motion in terms of force. Its mass resists changes in motion, but there's no force going back to the left here. All right, so I still am not entirely certain what to do here, right? So let's say I'm trying to find F, so you know I probably should do some of the forces in the x direction here for little m equals little m times a. So F minus Fn equals little m a. Obviously they're going to have the same acceleration. Okay, sum of the forces in y for this are 0. We don't want it to slide up vertically. So that means mu Fn minus mg equals 0. Okay. That's a given. That's an unknown. That's an unknown. So we're going to be able to eliminate Fn using this, right? So what's the normal force? Well, the normal force has got to be equal to, so I move that over here. So Fn has got to be equal to mg over mu, right? That's how big the normal force has to be. Oh man, my bad. Sum of the forces in the y equals 0, mu Fn minus mg equals 0, Fn equals mg over mu. So this is the frictional force minus gravitational force. Frictional force is up, gravitational force I said was negative. So the normal force has got to be equal to mg over mu in order to prevent sliding. So that is going to go up here in a second. So I could just do it now, I guess. Put it in there. F minus mg over mu has to equal ma. All right, so now we're down to two unknowns. Let's go look at the big M force diagram. All right, so sum of the forces in the x here has to be equal to big M times A. All right, so that means the normal force here has to be equal to big M times A. That's the only force acting in the x direction. Oh, huh. So what I can do now is put this all together. Maybe I should not have put this into there, all right? Oh, I guess I could solve this for A and put it in here. Maybe I could put this into here, solve for A, and then put it back in here. Oh, that seems like a good idea. So this all gets kind of crazy now. So this is equation 1 I'm going to call, all right? I'm going to put this now into here. I'm going to say mg over mu equals capital MA, so that A equals little mg over mu times big M. So I divided both sides by big M to get to here. Call that equation 2. All right, so I got this, then I went to the y direction, got this, put it back into here, and now I have this equation. I went over to this one, I got my acceleration here using this as well. This is really kind of a crazy one in terms of the algebra. So now we're going to plug 2 into 1. All right, so F minus mg over mu equals little m times little mg over mu times big M. All right, so bring this over to that side, so we get F equals little m times little mg over mu times big M plus little mg over mu. Then I'm going to factor out mg over mu. So if I bring that in front, mg over mu times little m over big M plus 1. That's probably how I would report that final answer there. Oof, that one's a tricky one, but I like it. It's a fun one.